we will now look into a few more aspects of reciprocal space and reciprocal lattice. So, effectively we look at more on Bragg's law and reciprocal space. So, we have 2D sin theta n lambda that can be written in a slightly different way by saying sin theta equals n lambda by 2 multiplied by 1 by d. Now, why did I write like that? We will know a little while later, because it is essentially to deal with how the appearance of the reciprocal lattice is and how we can get to these various values of sin theta from the d values for a given lambda. So, what we have done is we have already discussed the reciprocal lattice. So, some of the points which we should note from the Bragg's law are the following. So, in order to keep this discussion going and also to keep you afresh as we go further and further, is to remind you of the following points. One is sin theta is inversely proportional to d. So, this is seen here. Sin theta is a measure of the deviation of the diffracted beam from the direct beam. It is evident that structure with large d will exhibit compressed diffraction patterns, and conversely for small d. Let me take a little time to explain this. Suppose we have a structure with a very large d spacing. This is equivalent of having a multiple slit experiment, which we discussed earlier on. We discussed, of course, only a 2 slit experiment, and then we decided to increase or decrease the distance between these 2 slits. We can have a very large number of slits, many slits, some 8 or 9 slits. So, I can show you a little diagram of my own, which will be very lousy, but I will try to draw it. Suppose you have a source here, which is a light source, and then we keep a slit in front of it, we keep a screen in front of it, and then put holes through the screen 1, 2 and 3 and so on at equidistance. My diagram does not show equidistance, but you assume that they are all equidistant to each other. Then, as we discussed earlier on, each one of them now becomes a source. So, you will get spherical waves coming out from each one of those like that, and whenever there is an intersection here, we will get a bright spot on the screen which we are going to put here. So, we will get therefore the bright and dark images corresponding to these like that, and we know that it is an inverse relationship. So, the if the distance is d between these two, if that distance between these 2 points is a d and that is repeated in all in the 2-dimensional plane, then we will get a large number of indications of bright and dark lines here. That is the interference theory. So, what is said here is an issue where we can have different spacings of these slits or holes. So, each hole is a source. So, instead of this we can have a diffraction grating, which we have already discussed before, or we can have a crystal, which is essentially a 3-dimensional grating. And therefore, depending upon the type of d spacing we have, if we have a larger d spacing, what does it mean? What does it mean if you have a larger d spacing? Suppose 1 0 0 is a very large value, then 1 over d of HKL will be a very small value. If the value of a dimension is very large, suppose it is 20 angstroms, then the corresponding 1 0 0 plane will be at 1 divided by 20. So, as the unit cell expands, the expansion of the unit cell can go commensurate with the number of atoms which are put inside the unit cell. So, we can put, let us say, a protein molecule, the cell dimensions could be 100, 200, 300 or whatever, and they also go to their respective crystal systems depending on the symmetry with which they crystallize. On the other hand, if you have just an atom, the unit cell dimensions will be fairly small. So, for a smaller value, the 1 over d value will be very, very large, and for a larger d value, the 1 over d value will be very, very small. So, that means for larger unit cells, the number of points which you get will be a large number compared to smaller unit cells. You will get a smaller number. So, that is what is meant by this statement. So, the statement looks very profound, but essentially what it means is that we get a large number of reflections from a larger unit cell and a reasonable number of reflections from a reasonable unit cell and less number of reflections from a smaller unit cell. Obviously, this is not going to hurt our approach, because our approach would be to see as many information, as many scattering directions possible we will identify. That means as many d values we can accumulate, the better is the result. So, the idea of looking into reciprocal lattice further now will tell us how we can get this information and how useful that information can be. So, we therefore talk about the construction of a reciprocal lattice. So, it is based on 1 over d. See, we are talking about the d spacing here, that is the spacing on the screen here. 1 over d is the spacing which corresponds to the reciprocal lattice. So, when we get the reciprocal lattice image, the reciprocal lattice image is, we know that it is proportional to 1 over d. That is why the equation here is written in terms of 1 over d. Right. So, let us see a little detail of how these issues come up. Let us take a unit cell. So, let us take a unit cell here. This is, let us say, represents the unit cell. This is the origin of the unit cell. So, from the origin of the unit cell, if we now look at the planes which appear. So, suppose you take this as 0. So, 1 unit along this direction, you have this plane, and 1 unit. So, if you consider now the plane which is 1 unit away at 0, then we call this plane as 0, 1. We are looking into 2 dimensions. So, this plane will be 0, 1. The index of this plane will be 0, 1. So, we are looking at the diagram with respect to this background. So, we start from O, this is the direct space. We go up to that point which is 1 unit, and then 1 unit along this will represent the 0, 1 direction. So, if you now consider 1 unit along this and 1 unit along the second direction, then you will get a 1, 1 plane. That 1, 1 plane is represented in this fashion. So, 1, 1 plane is now going through this point. So, the similarly 2, 1 plane is now halfway along this. Remember the bread analogy. This is halfway along this and 1 unit down this. So, it will be 2 and 1. So, if you consider this plane, this is 3 and 1. Okay. So, we now therefore have represented 0, 1, 1, 1, 2, 1, 3, 1, the 4 planes with respect to the direct lattice. So, we have a direct lattice which has we have indicated the lattice diagram in the background. We have drawn those drawn the lattice net, and using the lattice net we have identified 4 positions 0, 1, 1, 1, 2, 1, 3, 1. These are the planes passing through with respect to the origin of the main cell. Now, the next step that is required is so what we have done is, next step is to draw normals to all possible direct planes from the origin. So, we have drawn now 4 direct planes 0, 1, 1, 1, 2, 1 and 3, 1, and we are now going to draw the all possible normals to these, draw normals. What do we mean by normal? That should come at 90 degrees to the diagram which we have drawn. So, you get a 0, 1 star, a 1, 1 star, a 2, 1 star and a 3, 1 star. So, these are now perpendicular. So, you draw the perpendicular to 0, 1, perpendicular to 1, 1, perpendicular to 2, 1 and perpendicular to 3, 1. So, these are now the stars are now the points which are normals which are drawn with respect to the various d of HKL. Now, where do we stop it? We have to have a stopping point, and the stopping point will be 1 over d of HKL. So, the length of each of these now is stopped at 1 over d of HKL. So, we know the value of the d of HKL now, and so the at 1 over d of HKL from this origin, this is now the origin of the reciprocal lattice. So, the origin of the reciprocal lattice is here. So, we now draw these lines normal to the various planes which we have shown intersecting at that point. So, this therefore will give us the collection of all the reciprocal lattice points which are indicated by star mark. So, reciprocal length and angles are designated by A star, B star, C star, alpha star, beta star, gamma star respectively, similar to the star marks on these values. So, these are the 1 over d HKL values. So, what we have to see also here is that whenever we consider planes in the two dimensional direct space, the plane was 0 1, the plane 1 1, the plane 2 1, this is a two dimensional case. The normals now are ending up with a point, and therefore, they are represented by points in the reciprocal space. So, when you get a diffraction pattern, we have already discussed that in the previous hour, that way with a diagram. Here again this diagram is making it more clear that from a diffraction from a plane is essentially like reflection, and so when X-rays fall on a plane, any point on that plane on which it falls will scatter at the same phase, and as a result the scattering direction is determined, and that scattering direction now is fixed at 1 over d of HKL, which now forms a point, and that is the reciprocal lattice point. So, if you take therefore a collection of all these reciprocal lattice points, in principle it also represents a 3-dimensional lattice, and therefore we call it as not just the points in the reciprocal space, we call it as a reciprocal lattice. So, given the direct lattice and the planes associated with the lattice, since the planes are associated with the direct space lattice, the points which are now normals to those planes, which are now the collection and the representation of the reciprocal space in reciprocal space, they define the reciprocal lattice. So, therefore, the reciprocal lattice, reciprocal points also form a 3-dimensional lattice. So, this is very important. They do not form a 2-dimensional lattice, they form a 3-dimensional lattice, because this direct space, these normals now are with respect to the planes. So, the planes are all in various orientations with respect to A, B, C, and therefore, we have the reciprocal lattice characterized by A star, B star, C star, and alpha star, beta star, gamma star are the interaxial angles. So, how does that develop? In what context we can see they are developing into these 3-dimensional lattices in various crystal systems. So, we will examine that a little carefully and closely, because that is something which will clearly tell us how this concept of reciprocal lattice has developed. It is not just that if we have A equals 100 angstroms 1 over A, how is it getting represented? Will it become 0.00 something? In fact, this question has been asked when we have taught several times by students. So, we thought we will make it clear in the context of how this is really coming up, and this two pictures will tell you clearly how this develops. The first picture tells us that we have a unit cell, and this particular unit cell is described with respect to the origin here. This is an orthorhombic direct space lattice. So, we have therefore OA is the distance along the A direction, OB is along the Y direction, and OC is along the Z direction. So, by definition the plane up here is 1 0 0. So, obviously by the plane, if you consider a plane at half point, it will be half, that is 0.500 the position, and this plane will be identified as 2 0 0, that is the Miller index revision. So, we can therefore have this as the unit cell. So, this represents now a ABC alpha beta gamma in this example is 90 90 90. So, how does the reciprocal cell come up? Reciprocal cell in this particular case comes up by this definition. The table below shows the relationship between the direct space and the reciprocal space associated with an orthorhombic unit cell. So, the unit cell dimensions are A, B and C. The corresponding dimensions will be A star, B star and C star. So, the point to note here is that the longest side in the direct cell, that is A here in this example, will be the shortest in the reciprocal lattice. So, we take the same origin, the origin is the same for the direct space lattice as well as the reciprocal lattice, and we now show the picture of the reciprocal lattice, that is we have already discussed and found out it is also a 3-dimensional lattice. And so, if there is a behavior of atoms and molecules in such a way that they are restricted to the orthorhombic symmetry, the symmetry that is reflected in the direct space must also be reflected in the reciprocal space. So, we therefore indicate this unit cell, this is A star, the short one becomes longer, it is B star, and this third one is C star. So, this will be now the unit cell of our reciprocal lattice. The fact that A, B, alpha, beta, gamma are 90 degrees will ensure that these values are equal to 90 degrees. What is also important to note is that they are interconvertible. That means, if you have A star, B star, C star as 1 over A, 1 over B, 1 over C, the corresponding ABC will be 1 over A star, 1 over B star and 1 over C star. So, what happens to the volume of the unit cell? The volume of the unit cell is A dot B cross C, and therefore, we can now calculate the volume of the reciprocal lattice, which is 1 over V, and that is A star, B star, C star. So, the volume also is inversely related to each other, and that is how this relationship develops. A very straightforward case in case of the orthorhombic symmetry. Any symmetry higher than orthorhombic symmetry, particularly if it is cubic, can also have this kind of a situation, or tetragonal will be a similar situation, because the angles alpha, beta, gamma are 90 degrees with respect to each other. So, crystals belonging to orthorhombic, tetragonal and cubic will have this feature: A star is equal to 1 over A, B star equals 1 over B, C star equals 1 over C, and so on. Remember, in the case of tetragonal and cubic, particularly in case of tetragonal, A is equal to B. So, your A star and B star will be one and the same from the distance point of view, but they are oriented at 90 degrees with respect to each other. Same thing extended to cubic system, A, B and C are all equal, and therefore, you will have 1 over A, 1 over A, 1 over A as the reciprocal lattice values for the reciprocal lattice in the cubic cell. So, otherwise the three crystal systems will have this kind of a behavior. So, this is the direct space lattice and that is the reciprocal space lattice, and the relationship between them is shown here. Now, we go to the discussion on the next crystal system, which is a monoclinic system. So, in the monoclinic system, we have a little bit of a deviation. The deviation comes because of the fact that beta is not equal to 90 degrees, considering B axis as the unique axis. So, once we consider B axis as the unique axis, the angle between A and C will be beta. So, beta is the angle between A and C, which is indicated in this diagram. So, we have the x, y, z directions indicated here. The x direction is taken up by A, the y direction is taken up by B, and the z direction is taken up by C. So, this volume of the unit cell will therefore be A dot B cross C. There is no change in that. Remember, I am using the vector notation. So, when I say volume of the unit cell is A dot B cross C, you should remember that there is a certain relationship between the involvement of beta as well in this calculation. So, let us look at what happens to the reciprocal lattice in this situation. The reciprocal lattice will be now differently oriented than the case of an orthorhombic system. It is not going to be coincidental with the directions of A, B and C, because now what happens is A star now will become, the reciprocal lattice will now be 1 over A sine beta. That is because we have to now consider the normal to the plane. You remember the previous picture where you saw the 4 normals being drawn to 4 different planes. So, we have to consider the normal to the plane, and therefore, if we consider the normal to the plane, this is the plane which is now this is AC projection, and therefore, if you consider this is the plane, this will be now the plane corresponding to the C axis, and therefore, if we now consider the d value associated with it, the d of 0, 0, 1 is perpendicular to this direction. So, therefore, this angle is beta, and we get the d of 0, 0, 1, which is the normal to the plane, not associated with the C axis. The normal to the plane is 90 degrees with respect to the plane, and therefore, we get this issue that we have now 0, 0, 1 in this direction, 0, 0, 1, 0, 0 is in this direction, because this is the 1, 0, 0 plane. If you consider here, this is the 1, 0, 0 plane. So, what you have done is you have taken the origin and drawn a line like that, and that is 0, 1, 0, 0. And similarly, along the B axis, you have taken and drawn a line like that, that is d 0, 0, 1. So, these two now will be making an angle, and because of the fact that we have a beta angle between A and C, the angle between d 1, 0, 0 and d 0, 0, 1 will also follow beta, but now that will be beta star. That is because it is going to be 180 minus beta. The reason is obvious. The reason it would have been ideally beta equals beta if it were 90 degrees. Since we now deviate from 90 degrees, this diagram is showing an obtuse angle greater than 90 degrees. The beta star will now be an acute angle. So that is because greater than 90 degrees, 180 minus 90, greater than 90 degrees will be shorter than 90 degrees. So we therefore get the beta star. So the conversion from A star to A star will be A star equals 1 divided by A. Now since this is involving beta, we bring in the issue of sine beta. How does that come about? This is drawn at 90 degrees. So this angle will come into picture, the beta angle, and you see that these two are at 90 degrees and these two are at angle beta, and therefore you get A times sine of beta, because the 90 degree angle is here and this is the value which we have to calculate. This is the angle beta, and therefore we get 1 over A sine beta. B star will be remaining the same because this is the direction of the two-fold axis. That means that both alpha and gamma are 90 degrees with respect to each other. So it will remain as such, like in the case of an orthorhombic system. So B does not change, B star will be 1 over B, whereas C star will follow the same diagram as we have here. So we get C star is equal to 1 over C sine beta. So this now is the representation of the reciprocal lattice associated with monoclinic systems. So if this is the case, then what happens to the relationship between these two? The reciprocal relationship will still remain, and in fact this should be beta star. There is a little error here. Maybe I will correct it right away. So this will be beta star, same as this. So A is equal to now 1 over A star sine beta star, 1 over B star and 1 over C star sine beta star. So you see that the volume of the reciprocal lattice is now somewhat shrunk with respect to the volume of the unit cell, because unit cell volume is ABC sine beta. It depends upon therefore this diagram. In this diagram you will see that the volume of the monoclinic cell with a beta value greater than 90 degrees will have a certain volume, and that volume will be different from the volume of the reciprocal lattice. I just want you to think about it and tell me which of these two volumes are bigger in terms of the values you have, because V star will be A star, B star, C star, sine beta star. Maybe you can take it as a numerical example. Let us say A is equal to 10, B is equal to maybe B is equal to 5 and C is equal to 12. So take a unit cell, A equals 5, B equals 10 or A equals 10, B equals 5 and C equals 12, and the beta angle you take it as 95 degrees or 98 degrees. So let me give you the values. A is equal to 10, the unit cell dimension A is 10, unit cell dimension B is 5 and unit cell dimension C is 12, okay, and beta angle you take it as 98 degrees. Calculate the volume. Now I want you to check whether the reciprocal lattice volume is smaller or larger. Okay. So you calculate the A star value, B star value, C star value, and find out what is the value of V star and see whether you can get to the value of V star. So what is important is to remember that beta star is of course 180 minus beta. So that will help you in this calculation. The reason why I want you to do it yourself at home is just to get an hang of how these relationships come up between the direct space and the reciprocal space, and how the unit cells now change over in case when we have the angles other than 90 degrees. I am not going to discuss the next crystal system in full detail, because obviously you see with one angle being away from 90 degrees it gets a little complicated. The case of triclinic is extremely complicated. So I will show you the diagrams which luckily for me is taken from the book of Stout and Jensen, which is a nice picture. In fact all these pictures are from that book, but the A star, B star, C star values and alpha star, beta star, gamma star values associated with the triclinic system, we will just take it for granted, and that is in the next slide. The next slide therefore shows you the triclinic direct and reciprocal cells. You see the complications. I didn't want to show you and then say it is complicated. You already anticipated the complication. So, we therefore have in this case A star, B star, C star values getting values of this kind, where you see that the volume of the unit cell still controls it. I think this diagram is already sort of giving way to what problem I gave you by just looking at it, but I want you to work it out. Okay. So, take the case of a triclinic cell, which is this is A, this is B, that is C, alpha, beta, gamma are all different from 90 degrees. And you see now again what we have to do is to draw normals to planes. So, when we draw normals to planes, these planes are not associated with any 90 degree angle, and therefore, they are acute or obtuse. Depending on alpha, beta, gamma being acute or obtuse, you will have the reciprocal lattice appearing something like this. So, it is not that when you say reciprocal lattice, the idea is to, this is nicely done by the book Stout and Jensen, nicely done in the book Stout and Jensen, because the idea is to give you that there is a dimension for the reciprocal lattice. You may think if there is a 100 angstroms, B 200 angstroms, then the reciprocal lattice volume will be very, very small, because it is 1 over A star, 1 over A and 1 over B. That is not the logic. The logic is shown here. The volume of the unit cell will be very different of the reciprocal lattice cell, and you can calculate the values of A, B, C, A star, B star, C star by using these expressions. And these involve so much of trigonometry associated with it. The orientation angles come in, and those go as products of cosine alpha, cosine beta, cosine gamma, and therefore, you will get these expressions. You see the volume now, which is simply again written as A dot B cross C in vector notation, will be equal to ABC and square root of this quantity, which involves the cosine square functions and also the cosine functions associated with alpha, beta, gamma. So, basically the take home lesson here in the last few minutes which we have had discussions is that we have different. So, I want you to also work out the case of hexagonal system, okay, hexagonal and trigonal. In both cases we have an angle 120 degrees. So, it is effectively like monoclinic. So, that is why I have not shown you. It is almost effectively like a monoclinic system, except that there are more conditions than in a monoclinic system. So, the angle being now gamma 120 degrees and not beta. The unique axis is along the C axis. So, the diagrams and the way in which you work out the direct space and the reciprocal space vectors and their corresponding volumes will be very similar, alike to or akin to what we do with a monoclinic system. So, let me recapitulate what we have done today. In this case, we started with the use of the Bragg's law and the reciprocal lattice definition. We indicated that as we increase the distance between between the planes, we find that the distances between the reciprocal lattice points shrink, and vice versa. And we also said that the once we have the 1 over d HKL values, we can directly generate the reciprocal lattice, and we showed with examples the generation of the reciprocal lattices with respect to various planes. And then we said that in case of the orthorhombic system, the monoclinic system, we calculated the direct space and the reciprocal space relationships, and also assumed the values associated with the triclinic system. This is all of it has been taken from the book of Stout and Jensen in this discussion, and I am very grateful to that book, because drawing these diagrams will be a very difficult task for me. The way I draw things you have already seen, it becomes a very difficult task for me. So, what do we do next? Next we will see what happens to Bragg's law in reciprocal space. This is something which we will take up in the next round of